Welcome to part 2 of 2, looking at the concepts of stability and balance. So in the last couple of videos we've just been looking at what variables tend to affect the stability and balance of an object. And in this one, the answer that we're going to try and see is the effect of the height of the center of gravity relative to a base of support. So in this scenario, we have two specific objects that both have the same exact mass. So if we say m is representative of the mass, whether it's 5 kilograms or 10 kilograms, both of these objects tend to have the exact same mass. They also have the same base of support. The only difference being is that the one is significantly taller than the other. So you would notice that there will be a difference in terms of their respective heights of their center of masses. Okay, so something that should be intuitively obvious is that if I were to apply a force to the top end over here, and I'll call that F1, and I were to apply a force to the top end over here, which I'll call F2, and both of these forces have exactly the same magnitude. So F1 is equal to F2. I'm just giving it different subscripts to denote that this one is being applied to object 2 and this one's being applied to object 1. Which one do you think would be easier to topple over? Intuition probably tells us that this one over here, object number 1, would be easier to topple over. But my question to you becomes, why is that the case? Okay, so again, we're going to try and just prove it with some basic maths. I'm not asking you guys to be able to prove it. I just want to make sure that at least the mathematics behind it all and the physics behind it all is at least making sense. Let's say again that it's going to be pivoting about a point. Both of these are going to be exactly the same. If I apply a force to an object which would cause it to rotate, it should be also fairly intuitive at this point that if I apply a force to this object, a distance from the center of mass and a distance from the axis of rotation, that this thing would cause a anti-clockwise rotation. Okay. The magnitude of that torque, so we'll call this torque object 1, is equal to the force that I apply, so this F1, multiplied by the distance that it is from the axis of rotation. In this case, remember it's the perpendicular distance, so it's R, and it's the perpendicular distance of the force to the axis of rotation. That's this. I'm not going to call it R, I'm just going to call it L to represent, it's basically the length of this particular object. So I'm just going to rewrite this as the torque force of object 1 is equal to the force multiplied by the length. Okay, so that should be fairly straightforward. In this case, same principle. It's kind of pinned here at the bottom. I'm applying a force. It's going to cause an anti-clockwise rotation, and coincidentally this object is exactly half as tall as that object. So if I'm still linking it to this concept of L, then this is simply L over 2, just half that specific length. Okay, so the torque on object 2 is equal to the force being applied to it multiplied by its perpendicular distance to the axis of rotation, which is just L over 2. Okay, so F1, if I'm just going to rewrite this, F1 is equal to torque divided by length, right? Just redistributing this to make F1 the subject of the formula. Over here, I'm saying that F2 is equal to torque divided by length over 2. Remember, if I have something divided by a ratio, then it's like multiplying it by the inverse. So this is simply equal to torque times 2 over L. or just to make it a little bit more intuitive, it's T over L times 2. Or hang on, let me just rewrite that as 2 times torque over L. Alright, well, since this, if I want to find out how much more force I have to apply in order to topple this over relative to this one for the same amount of torque, then I can simply substitute this F1 being equal to this torque over length into this torque over length over here. So F2 is equal to 2 times, and torque over length over here is equal to F1, so it's just F1. So in other words, it's saying that the force applied in this second scenario is twice as great as the forces applied in this scenario in order to cause this anti-clockwise rotation, or it's twice as difficult to destabilize this as it is to destabilize this. And it's something that we've spoken about before, from the fact that since torque is equal to force times distance, the greater the distance from the axis of rotation, the greater the torque, right? So the easier it is to topple over. If I were to apply, if I just had to restructure this whole scenario and say, if I were to apply a torque, a force over here, that same F2, right? If I were to apply a force through here, since this is still a given distance to the axis of rotation, it would also create a toppling over, but I'd have to apply twice as much force over here in order to get that torque than I would up here, right? So hopefully that's made some sense. In other words, a taller object is easier to cause rotation than a shorter object. The same way in previous examples when we've spoken about torque, that if I have an object rotating around some axis, the ease with which this tends to rotate is going to be dependent on where I apply a force. So if I apply a force over there, or if I apply a force a further distance, in scenario 2 the torque here is greater and over here it is less, or it's easier to cause rotation when I apply a force further from an axis of rotation. Same thing here, right? It's easier to cause this thing to topple over when I apply a force further from this axis of rotation. It's one of the reasons why shorter objects are more difficult to destabilize. Okay, so that's part 2.2, height of the center of gravity relative to a base of support. Notice that both of these had the same base of support, the same forces, and the same mass. The only thing that changed is basically the height of the object, the height of the center of gravity relative to the base of support.